Okay, let us consider section 2.1. In this section, we're going to introduce the concept of a hypothesis test. A hypothesis test is simply a framework for conducting the analyses that we've done thus far. Okay, let's go ahead and get started. A hypothesis test is a structured analytical procedure used to evaluate the amount of evidence or lack thereof for a research question. The amount of evidence or lack thereof is based on probabilities, and a hypothesis test is done so in a very consistent and structured way to ensure that two different statisticians would arrive at the same conclusion. The first step in conducting a hypothesis test is the identification of the research question. We will consider three case studies that we've looked at previously. The gender discrimination case study. The question of interest or research question was, is there evidence of discrimination against females for those chosen for a managerial position within this company? In section 1.2, we considered the staring case study. There, the question of interest was, is there enough evidence to say that the woman in this study has the ability to correctly identify when somebody is staring at her? In the ear infection example, the question of interest was, is there enough statistical evidence to say there is a difference in the duration of ear infection between the breastfed and bottle-fed babies? In general, the research question determines exactly what type of statistical analysis is appropriate. Therefore, it is important to identify the research question and ensure that it is clearly stated so that the appropriate analysis can be completed. We will now consider two definitions. The first, scope of inference. Scope of inference is simply to whom the study outcomes, and hence the conclusions, apply to. The parameter is a numerical value that is being tested by the hypothesis. The parameter is what is used to build the simulation model. This value is determined by pi, not to be confused with the mathematical constant of 3.14. For each of these case studies under investigation here, we will next identify the appropriate parameter of interest. For the gender discrimination example, the management pool contains 60% female and 40% male. The parameter here is the probability of a female being selected for a management position under a situation of no discrimination. If the management pool contains 60% females, then under no discrimination, 60% of the individuals chosen for a management position should be female. Therefore, the parameter value is set to be 60%. Pi is equal 60%. In the staring example, the parameter is identified to be the probability that a woman in this study could correctly identify when being stared at, under a situation of no ability. So if that woman had no ability to identify when somebody was staring at her, she would simply have to guess. She'd have to either select look or no look. And then from that, we would determine whether or not she was correct or incorrect. But in a guessing situation, she has a 50-50 chance of being correct. Therefore, the parameter value for the staring example is set to be 50%. In the ear infection example, the parameter would be the probability that a breastfed baby would do better than a bottle-fed baby in a head-to-head comparison, again, under the situation of no difference. If there's no difference between the breastfed and bottle-fed babies, then either one is likely to do better. Therefore, the parameter value for this particular case study is set at 50% as well. Okay, let us now consider the scope of inference. In the gender discrimination example, we were trying to make conclusions about women who were seeking a managerial position within this company. Therefore, that is the scope of inference. Now, it is important to identify that we are just trying to make decisions about women within this company and not some other company. Therefore, our scope of inference is women who are seeking managerial positions just within this company. In the staring example, there's only one woman that completed the study, or at least we were being asked to evaluate whether or not that one woman had the ability to identify when somebody was staring at her. We only gathered data on that one woman. Therefore, the scope of inference is simply the one woman in that study. How about the ear infection example? The ear infection example is a bit more difficult. Certainly, the scope of inference is babies that are breastfed and babies that are bottle fed. However, it is difficult to determine exactly what or whom the scope of inference is because we do not have information about how the researchers decided upon which babies to put in their study. Without that information, we don't really know who the scope of inference is. For example, we don't know if they used babies from all over the world, or did they just use babies from a particular area, say in New York City, or even more focused, maybe babies from a particular hospital. If you're selecting babies from just one particular hospital, then the scope of inference applies to just that one hospital. Okay, how about section 2.1.3? Here we're going to introduce the concept of a null hypothesis and an alternative hypothesis. In the null hypothesis is what the outcome from your study is being compared against. Okay, so the null hypothesis is what the outcome from our study is being compared against. The null hypothesis determines exactly how our simulation model will be set up. The parameter value of interest will go in the null hypothesis. The alternative hypothesis is simply the research question. So a restatement of the research question through the use of a parameter is placed in an alternative hypothesis. Let us now consider the case studies. For the gender discrimination, the research question was, is there evidence of discrimination against females for those chosen for a managerial position? Now, the alternative hypothesis is where the research question is placed. So we were curious of whether or not there is discrimination against females. If that's the case, then the selection process is biased against females. And in particular, the parameter value would actually be less than 60%. Whereas the null hypothesis is where the parameter value being used to develop the simulation model is placed. The null hypothesis for the gender discrimination case is that the selection process is fair and that there's no discrimination. If we put these in symbols, as we have over here on the right-hand side, the null hypothesis, denoted by H0, is that the parameter value is set to 60%, whereas the alternative hypothesis, again specifying that there's discrimination against females, that parameter value would actually be less than 60%. How about the staring example? The research question was, is there enough statistical evidence to say the woman in the study has the ability to correctly identify when somebody's staring at her? Again, let us consider the alternative hypothesis first. The alternative hypothesis would be that the probability that she can correctly identify when somebody's staring at her is actually greater than 50%. If she does indeed have the ability, then the chance of her getting a correct result should be greater than 50%. The null hypothesis in this case would be that the woman is just guessing. The null hypothesis is identifying the situation of no ability. So the parameter value there would have to be set to 50%. How about the ear infection example? In the ear infection example, the research question was, is there enough statistical evidence to say there is a difference in the duration of ear infection between the breastfed and bottle-fed babies. The alternative hypothesis for this case study would be stated as there is a difference in the duration of fluid between the breastfed and bottle-fed babies. In particular, that parameter value would have to be something different than 50%. The null hypothesis is the situation of no difference. So there, the parameter value would be equal to 50%. That, the designation of the null and alternative hypothesis, written in terms of the parameter, is provided here on the right-hand side. Again, the null hypothesis is that rate in which there's a difference between the breastfed and bottle-fed babies. Okay, that parameter value is set to be pi here. So if there's no difference, it's going to be a 50-50 situation. Whereas if there is a difference between them, then that parameter value is going to be something different than 50%. Notice that for the gender discrimination, we were worried about that parameter value being less than 60%. In the staring example, we were curious of whether or not that parameter value in the alternative hypothesis was greater than 50%. And in the ear infection example, we were curious whether or not that parameter value was something different than 50%. Okay, how do we obtain the reference distribution, given this information about the null and alternative hypothesis? It's pretty straightforward. The null hypothesis is what is being used to set up the simulation study. So in the gender discrimination case, the parameter value under the null hypothesis was 60%, and therefore the simulation setup, the probability of success value that we use in building our simulation, is that parameter value of 60%. In the staring and ear infection examples, the probability of success would be specified as 50%. It is simply the value that is provided in the null hypothesis. So again, the value in the null hypothesis is what determines how the simulation is set up. Okay, a quick comment. The research question must be stated in a way that a simulation model can be set up. Some hypotheses are actually not testable. We cannot do a hypothesis test in some situations. Let us consider the ear infection example. In version A, provided here, the research question was the one that we considered up above. Is there enough statistical evidence to say there's a difference? We set up the hypothesis as I'd done up above, with the parameter value being 50% in the null hypothesis, and the parameter value being something different than 50% in the alternative hypothesis. Let us consider a slightly different version of that research question. Is there enough evidence to say that there's no difference in the duration of ear infection between breastfed and bottle-fed? So all we've done here is simply turned or reversed what we put in the null and alternative hypothesis. Now, this hypothesis cannot be tested in a statistical way. Let us consider why. The reason the research question B is not a valid research question is simply because we cannot identify what the appropriate reference distribution is. If the reference distribution and the simulation model is to be set up under the null under the null hypothesis, then that has to be something different than 50%. Over here on the left-hand side, I've certainly identified a parameter value that's different than 50%. In particular, I've identified it to be 55% in this. The sample size is 23 for this example, and I obtained 1,000 different simulated outcomes. The expected value for this particular situation would be 12.65. Simply take 23 and multiply it by 0.55. This simulation model here is set up under the null hypothesis. But I can set up another one as well under the null hypothesis. Here I've specified the parameter value to be 0.83. Again, certainly different than 50%. And what happens is that reference distribution gets shifted up. It's not at 12 anymore, but now it's shifted up to 19 because my parameter value here is much higher. I could develop yet a third situation under the null hypothesis. A probability of success or a parameter value of 62.35% would work as well. The expected value in this situation is 14.34. I have three different reference distribution or simulation models that are set up under the null hypothesis. Which one of these three are we going to use to evaluate our evidence or to evaluate the study outcome? The issue here is that there are several, in fact, there are infinite many different simulation models that we could set up. And therefore, there's no fair way to determine which one to use in evaluating the evidence from the study. Therefore, it is not possible to use this framework to consider the research question posed here in Part B. That's not a hypothesis that can be tested using the methods that we are talking about here. Okay, let us consider the reference distributions. We've used this term loosely, but now I'll carefully consider what I mean by a reference distribution. A reference distribution is just a graph of the outcomes from many repeated trials. These outcomes are used to measure and evaluate the amount of evidence the data provides for the research question. The three reference distributions that we've been considering, the gender discrimination, the probability of success for that one was 60%, sample size was 20, and this would be the reference distribution that is obtained, again under the null hypothesis. For the staring example, the probability of success there was 50%, with a sample size of 20. The expected value here is 10, and we can see the reference distribution there for the staring example. For the ear infection example, the parameter value was again 50%, but the sample size was 23. And this is the reference distribution that is obtained from that simulation model. The determination of appropriate cutoffs, and also our ability to measure the amount of evidence, is going to be obtained through these reference distributions that we've been using up to this point. Okay, let's talk about making a formal decision. I introduced the outlier rule and stated that the outlier rule uses the commonly accepted 5% level. This 5% level actually was designated or first introduced by somebody called R.A. Fisher. R.A. Fisher is actually the grandfather of modern statistics. He made a statement that 1 in 20 was convenient to use as a limit in judging whether or not an outcome was statistically unusual. This occurred, or this statement was made, clear back in 1925. And to this day, we still use this 1 in 20 as our standard when determining statistical significance. 1 in 20 is indeed 5%. Therefore, the widely used value in determining whether or not we have statistical significance is 5%. A little bit about the tail of the distributions. In the gender discrimination example, we wanted to know if there was gender discrimination against women. That meant that we needed to be on the left-hand side of the distribution. If we were too low in this distribution, then that indicated evidence of discrimination against females. In the staring example, we were interested in whether or not this woman was too high on her number line. If she was too high on the number line, then that would provide evidence that she did have the ability to identify when somebody was staring at her. In the ear infection example, we actually had interest in both ends of the distribution. Recall in the ear infection example, we were tracking the number of times breastfed wins in that head-to-head comparison. If we were too high, if we were on the high end of that distribution, that meant that we had evidence for breastfeeding doing better. If we were too low on that number line, that would indicate that bottle-fed kids were doing better. The important thing to note here, though, is that both ends of the distribution provide evidence for the research question. And hence, when determining cutoff values, we must consider both sides of the distribution. What do we mean by a left-tailed test or a left-tailed analysis? A left-tailed test simply means that interest lies in the left edge of the reference distribution. Likewise, a right-tailed test is when interest lies in the right edge of the distribution. And two-tailed simply indicates that we care about both tails of the distribution, either being too high or too low. So the gender discrimination example is an example of a left-tailed test. The staring example is an example of a right-tailed test. And the ear infection example is an example of a two-tailed test. How do we make a formal statistical decision then? Well, if the outcome from the observed data is within the bottom 5%, or the top 5%, or the outside 5%, then we say that the data provides enough statistical evidence for the research question. If the outcome from the observed data is not contained in the bottom, top, or outside 5%, therefore it's not an unusual outcome, then we must conclude that the data does not provide enough statistical evidence for the research question. Okay, next, let us talk about measuring the amount of evidence. When we want to measure the amount of evidence, we use the notion of a p-value. So what is a p-value? A p-value is the probability of observing an outcome as extreme or more extreme than the observed outcome. The p-value clearly measures and identifies the amount of evidence that an observed outcome from a set of data provides for a research question. The p here in p-value simply stands for a probability. All probabilities must be between 0 and 1. Therefore, a p-value cannot be less than 0, nor can it be greater than 1. And when we say as extreme as or more extreme, what we are talking about there are outcomes that would provide additional support for the research question. So when determining the p-value, we need to worry about what values provide even more support for the research question. Let us compute the p-value in the staring case study. Recall, the research question in the staring case study was, is there enough statistical evidence to say the woman in the study has the ability to correctly identify when somebody's staring at her? The parameter here is the probability of a correct guess by the woman in the study. We've talked above about the appropriate setup of the null and alternative hypothesis. We've identified this as a right-tailed test. Again, values, why is it a right-tailed test? Because we wanted to know whether or not she had the ability to identify when somebody was staring at her. If she did indeed have the ability, then she should have more outcomes correct than what we would expect by chance. The observed outcome from the study was 14 out of 20. Now, let us identify the values that will be needed for computing the p-value. So, what values are as extreme or more extreme than 14 when she has the ability to identify when somebody's staring at her? Again, when we use the terms as extreme or more extreme, what we mean are what values would provide even more evidence for the research question than the study outcome obtained. Again, if she had the ability, then values as extreme or more extreme would be 14, that's as extreme, 15, 16, 17, 18, 19, and 20. So these values, 15 through 20, are values that are even more extreme than the study outcome. That would provide evidence for the research question. Let us now get the p-value from the reference distribution. As I've stated, the probability of success would be 50%. The sample size here is 20. And I need to obtain the probability or the chance of seeing values as extreme or more extreme than the study outcome. As we've just stated up above, those values would be 14, 15, 16, 17, 18, 19, and 20. These values that are indicated in red here. If I place the study outcome in the as extreme as box and click the count button, what that reference distribution app does is it computes how many of the 1,000 dots, okay, I think I used 1,000 dots here, how many of the 1,000 dots are at 14 or more than 14. And the app has determined that to be 58. So the probability here, or the p-value, is simply 58 divided by 1,000. Again, this reference distribution was determined using 1,000 dots. And 58 of the repeated outcomes from the simulation study are at 14 or something greater than 14. Therefore, the p-value would be computed as 58 divided by 1,000, or 0.058, which is 5.8%. How do we make a decision using p-values? Well, the decision rule for p-values requires us to compare the p-value against that standard guideline of 5%. In particular, if the p-value is less than 5%, then we can say that the data provides enough evidence for the research question. If the p-value is not less than 5%, then we must conclude that the data does not provide enough evidence for the research question. Let us consider a moment what this p-value represents. The p-value represents the chance that I'm going to see something 14 or greater under a situation, okay, under the situation of no ability. Remember, the simulation distribution or the simulation model is built under a situation of no ability. So there's about a 5.8% chance that somebody with no ability will get 14 or more correct. 14 does not sit in the top 5%. It actually sits in the top 5.8%. Therefore, 14 is not an outlier. We can come to the same conclusion by just determining and looking at whether or not the p-value is less than that 0.05 or is less than 5%. So the p-value makes its decision in exactly the same way that the outlier rule did. The p-value, though, simply requires us to compare that percentage that we obtained against 5%. If the study outcome was way out here at, say, 18, the p-value is actually going to be quite small because I don't have any dots out here at 18 and above. And certainly we would agree that 18 sits in the top 5%. So again, the p-value approach to determining whether or not I have enough evidence is equivalent to the outlier rule approach in determining whether or not we have enough evidence. The nice thing about a p-value is it actually provides a measure for the amount of evidence. We can see that 14 is actually pretty close to the top 5%. It actually sits at the top 5.8%. Okay, let's just take a minute to talk about the decision rule. This decision rule is very strict. If the p-value is less than 0.05, then we say we have enough evidence. So if the p-value was 0.0499, we would have enough evidence. However, if the p-value was 0.051, technically a statistician would say we do not have enough evidence. So we use that 0.05 threshold pretty strictly, which for me is not optimal. I'd like a little bit of leeway there in that 0.05. If it's close to 0.05, then I might say that we have enough evidence. Likewise, if it's far away, then I would say we don't have enough evidence. However, I'm not the first person that has thought about this. And in particular, Bross, a long time ago, discussed this. If we allowed people to identify, say, values around 0.05 as maybe marginal evidence, and then values that were real small, p-values that were real small as strong evidence, we would just have people arguing over what we mean by strong evidence and what we mean by marginal evidence. In fact, we would actually have two cutoffs that we'd have to worry about here in evaluating the amount of evidence. So even though I don't like real strict rules for determining whether or not something supports the research or doesn't support the research question, we must appreciate that there is a standard, and that standard is used by everyone. It does not matter if you're in biology, if you're in sociology, if you're in a business school or in a law school. Everybody uses the 5% rule when evaluating statistical evidence. So that's actually kind of nice, if you stop and think about it, that everybody uses that same standard. Okay, let us continue with finishing up that staring case study. The p-value, computed up above, was 0.058, 5.8%. Is that p-value less than 0.05? It's not. So we got to ask ourselves, is 0.058 less than 0.05? The answer to that is no, it's not. If the answer to that is no, then we do not have enough evidence for the research question. So the data provided does not provide enough evidence for the research question. That's the decision of the test. How about a conclusion? The conclusion, okay, in writing conclusions, we want to simply in layman's terms, discuss what we've learned by completing our analysis. And a conclusion can be divided up into three pieces. Let me identify those three pieces. The data does not provide enough support. Okay, so that's the first piece here. The data does not provide enough support. This is simply the decision that we arrived at up above. The first part of the conclusion simply identifies whether or not the p-value was less than that 0.05 threshold. So this first part is the decision. The second part then is simply restating the research question. That research question for the staring example was, let's go back up and look at it. Is there enough evidence to say that the woman in this study has the ability to correctly identify when somebody's staring at her? Okay. So the research question here to say, oops, let me fix that maybe. So the data does not provide enough support to say that this, let me fix this here before I go any further. The data does not provide enough support to say, okay, I think I got that cleaned up. So again, the first part is the decision. Okay, that's this part here. The data does not provide enough support. The second part is the research question, which is this here, to say that the woman in the study has the ability to correctly identify when somebody's staring at her. And then the third part of the conclusion is just a provide the p-value. Okay, remember that the p-value is the amount of evidence that we have for our research question. And it's kind of nice to provide that in the statement that we're making about the research question. Therefore, the reader will have an indication of whether or not or how close this is to that 0.05 threshold. So again, there's three pieces to writing a conclusion. Let's just identify those here with three different colors maybe. When I'm evaluating whether or not conclusions are correct in your homeworks and assessments, these are the three pieces that I'm going to be looking for. The decision, a restatement of the research question, and then the amount of evidence that you have for the statement that you're making. Those three pieces, and you have a correctly written conclusion. All right, let us do one more example in computing the p-value. We'll do this one more quickly. This is the ear infection case study. The research question here, is there enough statistical evidence to say there is a difference in the duration of ear infection between breastfed and bottle-fed babies? Again, this is a two-sided example. We talked about that up above. It's two-sided because being too high in the number line is going to indicate a difference, and being too low in the number line is going to indicate a difference. So when determining values as extreme or more extreme than the observed outcome, what we need to do is worry about 16 and above. Certainly if there were 17 instances in which breastfed won, then that would be more extreme than 16. 18 would certainly be more extreme than 16. So in computing the p-value, I need to worry about the values on the high side. I need to worry about values 16, 17, 18, 19, 20, 21, 22, and 23. When looking at the distribution, 0 certainly is more extreme than 16. Remember, the reference distribution is going to be centered here in the middle. So 0 is certainly more extreme than 16. Also, 0 provides evidence for this research question. So when computing the probability value or the p-value, I need to compute how many dots, or I need to look at the likelihood of 0. I need to look at the likelihood of 1, 2, 3, 4, 5, 6, and 7. Now, how do I know that I need to stop at 7? Okay, again, we need to worry about how far away is 16 from the middle of the distribution. So let me just make a note of that. We stop at 7 because 16 minus 11.5 is equal to 4.5. Okay, so 16, or the study outcome, is 4.5 above the expected value. 7 is 4.5 below the expected value. So that's the corresponding value of 16 on the lower end. Now, to be honest with you, we don't have to worry too much about this because that respective value on the lower end is automatically determined in our reference distribution app. So let's look at that. For this example, this is a 50-50 example, sample size being 23. What's being tracked here on this number line is the number of times breastfed wins out. When determining as extreme as, I'm going to want to put my study outcome in this box. However, because this is a two-sided problem, I'm going to want to make sure and select the two-sided icon in the lower left-hand corner of the app. That is going to compute two different probability values for me. It's actually going to combine those two probability values. So the probability of the probability of observing 16 or more is 54 out of the 1,000. Again, I have 1,000 dots on this distribution. 54 of them sit at 16, 17, 18, 19, 20, 21, 22, and 23. Okay, 54 of the 1,000. That's being indicated over here by the app. So the p-value on the upper side is 0.054. As stated above, the corresponding value on the lower end of the distribution is 7. So what proportion of the dots sit at 7 and below? Well, there I have, according to the app, 52 dots. 52 dots out of the 1,000. So the p-value on the lower end is 0.052. For a two-sided analysis, I need to add both of these probability values together. And when I do that, I get 0.1060, or 10.6%. And this is precisely the value that is computed here by the reference distribution app. So now let's apply the decision rule. The decision rule is, if the p-value is less than 0.05, then we have enough evidence for the research question. So is 0.106 less than 0.05? The answer is no. So once again, this example does not provide enough evidence for the research question. Let's go ahead and write a conclusion that has the three parts that are required of a conclusion. So the data does not provide enough evidence to say, okay, that's the decision here. Now we need to go get the research question. And the research question here is to say that there is a difference in the duration of ear infection between breastfed and bottle-fed babies. So I'm just going to copy and paste that right in here. So the data does not provide enough evidence to say, the research question is next, that there is a difference in the duration of ear infection between breastfed and bottle-fed babies. And the third component is just to provide the p-value, which is 0.106, which is 10.6%. Again, those are the three elements of the research question: the decision, the research question itself, and then the amount of evidence that you have. So those three pieces, oops, sorry about that, those three pieces, and you have a successfully written conclusion. Okay, that does it for section 2.1. In the next section, we will look at more examples of computing p-values. Okay, thank you.